All right, here we go. So we're going to look at numbers 10, 12, and 13 from your textbook and hopefully get a little bit more comfortable with these ideas. So here we go. The first one, question number 10. Notice that these questions, most of them deal with either the Q equals MC delta T. Remember, this is when we have heat that is going into or coming out of a substance and it's causing a change in temperature. The change in temperature depends on the mass. Obviously, if you have more mass, it takes more heat to heat it up. And then C is the specific heat. The specific heat is different for each material. Some materials have a low specific heat, which means that it heats up fairly quickly, and some have a high specific heat. Specific heat, remember, is the amount of energy required to raise 1 kilogram of mass 1 Kelvin or 1 degree Celsius. Okay? The other one that we'll use a lot is this Q equals ml. Right? This is, again, the heat coming in or the heat going out, causing a certain mass to change phase, to completely change phase. So the L is what we call the specific latent heat, and that's what's required to get it to change phase. All right? So we do have some information in a table. We'll get what we need as we go. So the first question, how much heat is required to raise the temperature of 250 grams of copper from 20 degrees to 160 degrees Celsius? All right, so for this, the question is how much heat. So it's actually looking for Q there. It does give us the mass. The mass is 0.250. Remember, mass needs to be in kilograms. Okay, if in question, if you look at C, C is the specific heat capacity, which if you look at the units of specific heat capacity, that is also in kilograms. So therefore, my mass needs to be in kilograms, so it cancels out. So that times C, so I'm going to look for C for copper, which is right here. It's 380, all right? And then the delta T. So delta T is always final minus initial, right? So T final minus T initial. Now, because I'm finding the change, then I can use either Celsius or Kelvin here. Because Celsius and Kelvin, each degree is the same distance from each other. And the difference in two temperatures Kelvin is the same as the difference in the same two temperatures Celsius. And so we can go ahead, you can do 160, which is the final temperature, minus 20. Okay? If you were to turn that into Kelvin, you would need to add 273 to each of those. But when you subtract, that 273 is going to end up canceling out anyway. All right? So from this point, all you have to do is go ahead and put those numbers in. So we just go 0.250 times 380. I always do that. 380 times, and then I'm going to put in parentheses 160 minus 20. And we push enter, and we get the final answer that the amount of heat required is 13300, and that would be its heat. So that's energy, so that would be in joules. All right. Our next question, we're going to go up to number 12. Okay. We're not doing every single one of these questions, so we'll jump up to 12 here. So we'll go question 12. A 500-gram piece of aluminum is heated with a 500-watt heater for 10 minutes. How much energy will be given to the aluminum in this time? Okay, well, it tells me that there are 500, the heater is 500 watts. Okay, now watts, remember, is power, and power is energy over time. So watts is 500 joules per second. So if that's joules per second, and it runs for 10 minutes, then I just need to figure out how many seconds that 10 minutes is. So 10 minutes, there's 60 seconds in a minute, so I'm going to multiply by 60, and I get 600 seconds. So if I have 500 joules per second, then if I multiply by the time, which is 600 seconds, then I just multiply 500 times 600, and I get 300,000 joules. right? Now, if you wanted that as an equation, it's simple enough. They do tell us that power equals change in energy over the change in time. So we've got the power, which is 500 watts. You've got the time, which is 10 minutes, which you need to put into seconds. And then you should be able to solve for the energy just like that. Okay, so you could do simple unit conversions. You could also use this formula to help you figure that out. Now, in part B, the question says, if the temperature of the aluminum was 20 degrees at the beginning, what will its temperature be after 10 minutes? Well, we know that when we have something changing temperature, that we're using this Q equals MC delta T, right? Now, we just found out how much energy there was, right? We just found out that it was 300,000 joules. So I can go ahead and put that in. I'm going to put it in joules. I'm not going to put it in kilojoules. So 300,000 joules. That should equal the mass. The mass was given in the beginning of the question, which was 500 grams. So we're going to go 0.500 kilograms. Then we'll multiply by the specific heat. The specific heat we can look over here, which is 900 joules per kilogram per Kelvin. And so we'll multiply by 900 there. And then the change in temperature. Change in temperature is the final minus the initial. So I don't know what the final is, but I do know that the initial is 20. Now notice that this is degrees Celsius, which means that when I get my final answer, that will also be in degrees Celsius. Anytime you're finding a change, a difference, you can use either Celsius or Kelvin. Okay, so it doesn't ask for Kelvin or Celsius, so I can go ahead and work with Celsius here. Please do remember this, because if it just has a T in it, right, you may have learned in class about the Boltzmann constant, the Kb, and the ratio with that. That's just a T, right? That the wavelength depends on T. And so if the wavelength depends on T, or if the kinetic energy depends on T or whatever else, that T must be in Kelvin because it needs to go through 0, 0. So with that, we can go ahead and solve for this. I'm going to take my 300,000. I'm going to divide by the 0.5. And then I'm going to divide by the 900. Just like that. And so I now have 666.6, and then repeating sixes until I get down to the 7, is equal to the final temperature minus 20. I'm going to add 20 to both sides, and that should give me my final answer, which it looks like I had 3 significant figures up there. 500 is technically just one significant figure. That's really just one. That's really just one. So I guess really my answer should be 700 degrees Celsius. I'm going to go ahead and write down 687 degrees Celsius, but recognizing that if I were to do this in significant figures, it should be 700, okay? Because that's all I have is one significant figure for each of those, okay? So that's letter B, and that's question 12. Let's move on. I was going to do 10, 12, and 13. So let's look at question 13 here. So you'll notice that none of this is overly difficult. It's not, they haven't done anything super challenging with these formulas yet. It's just getting kind of used to them, getting comfortable with them. The challenge is going to come in class. All right, so Q13, a car of mass 1,500 kilograms traveling at 20 meters per second brakes suddenly and comes to a stop. How much kinetic energy does the car lose? All right, well, we can go ahead and start with the idea that we know that the mass of the car is 1,500 kilograms, and we know that the initial velocity of the car is 20 meters per second. And it does say that it slows to a stop, which means my final velocity is 0 meters per second. Now, the first question is, how much kinetic energy does the car lose? Okay, well, to find out the kinetic energy of the car lost, I need to find out how much it started with, right? So the kinetic energy that it started with is going to be equal to 1/2 mv squared. So 1/2 times the mass, which is 1,500, times the initial velocity, which is 20 squared. And so I can do that. I can go 0.5 times 1500 times 20 squared. And I end up getting, oh, that's interesting, same number as we got last time. It's just a coincidence. It's okay, those things happen. But we get 300,000 joules. All right, so that would be the kinetic energy at the beginning. We know at the end the velocity is 0, which means it has no kinetic energy at the end. So if I started with this much, then the total change in the kinetic energy would be negative 300,000. And I know some of you say, but Mr. Bauer, it doesn't say negative. Okay, well, but remember, to get a change, it's final minus initial. The final is 0, so it's 0 minus 300,000. You could also think of it this way. The minus represents the fact that the change is negative. The change is a loss. If you have a positive, you expect that to mean a gain. Okay, so we do want to make sure that we're consistent with that and that it makes sense with our context. So that would be the answer to question A. All right, if we move on to question B here, all right, question B says, if 75% of the energy is given to the front brakes, how much energy will they receive? Well, that's pretty straightforward. We just have to take that and say, well, I want 75% of that, which is 0.75. And when you multiply by 0.75, we do get an answer of 225,000. Okay. Now that 225,000 could be for a variety of different reasons. It could mean because there are brakes in the front and the back, so some of the energy is going to the front, some is going to the back. It could mean that the tires are sliding a little bit on the ground, right? In which case we'd lose some heat to the ground. It could have something to do with efficiency, that the brakes are only that much efficient, and so some of the energy isn't actually given to the front brakes. Some of the energy goes somewhere else, right? To the engine or something else. And so that 75% could be a number for a number of different reasons. Now, you remember we did a question in the initial video, 1, 2, 3, 4, in which we calculated and we kind of ignored that. This is a little bit more realistic, that not all of the energy is going to go directly to the brakes. All right. So here, C, the brakes are made out of steel and have a total mass of 10 kilograms. By how much will their temperature rise? All right, so now we're getting to one of these MC delta T ML. Well, it's definitely not undergoing a phase change, so we're doing this MC delta T here. Okay, so we're saying the heat going into the brakes is going to be equal to MC delta T. Okay, now the question is, how much will the temperature rise? So we're actually looking for this. So you don't need either of the temperatures. We're just finding how much it will change. The Q is that 225. The mass is, it gives us that. The mass is 10 kilograms. And the C, it did say it was steel. So if I go over here, I can look at steel, and steel is 440. So go 440 and then times delta T. And from there, I should be able to take the 225,000. Okay, that's what I have here. I'm going to divide by the 10, and then I'm going to divide by 440, and we do get 51. So the change in temperature is 51.1 degrees Celsius. Okay, now that's a pretty big change for the brakes, but the brakes do heat up. Now, if you've ever driven a car down a mountain before, you may have been in the situation where if you use the brakes too much, you can actually start to smell the brakes. The brakes actually start melting because the energy gets so high, right? This was just slowing down from 20 meters per second, right? But if you start with a whole bunch of kinetic energy at the top of a mountain, as you go down, all of that needs to convert to kinetic. And if it's not going to kinetic, it must be going somewhere else. If you're constantly using the brakes to slow it down, kind of like what we were talking about in this question, in question 4, where we had a block sliding down a ramp, and some of the energy was going to the block, to the thermal energy between the block and the ramp due to friction. Same thing here, the temperature can increase, and you do it again, it increases more, and eventually you get to the point where you have a very large change in temperature, and the brakes can heat up to a point where they start to melt and deform. All right, so anyway, just kind of an interesting connection. I think this is the answer to C, and that is all that you had to do in tonight's homework. I hope that was helpful, whether you needed to just check your answers or whether you were using it as a help to understand what was going on. And I'll see you next time.